Every generation ship humanity could realistically build would need to survive for centuries, sealed shut, with nothing behind it but the memory of Earth. Proxima Centauri, the nearest star system to our own, sits 4.24 light-years away. At the fastest sustained speed any spacecraft has ever demonstrated, reaching it would take more than 6,000 years, roughly 250 human generations, born, raised, and buried inside the same hull. But here is what most people get wrong. The hardest part was never the distance. It is keeping a sealed civilization alive, breathing, governed, and reproducing itself longer than most nations in history have lasted on solid ground. If this kind of deep engineering mystery grabs your attention, do me a favor and hit that like button, and if you have not subscribed yet, now is a great time. Now, let's begin. Somewhere, on paper that has never left a drafting table, there is a door. Behind it, a corridor curves gently upward, the way the floor of a very large wheel would curve if you stood inside it. There are quarters along that corridor, kitchens, a school. A child runs down the hallway toward dinner, the way children do, and never once looks up expecting to see a sky. She has never had a reason to. The ceiling has always just been the ceiling. This is the idea at the center of a generation ship, not a rocket, not a shuttle streaking somewhere and coming home. A vessel built the way a nation is built, meant to outlive every single person born inside it. Here is the detail that separates it from almost every other interstellar concept ever proposed. A generation ship does not carry its crew to the destination. It carries a population, and that population reproduces itself along the way. The people who leave Earth are not the people who arrive. Their descendants are. 3 generations removed. 5, sometimes dozens, depending on how far the ship is going and how slowly it has to go to get there. The idea itself is over a century old. In 1918, the rocket pioneer Robert Goddard wrote an essay called The Ultimate Migration, describing a ship that would leave a dying solar system with its crew in suspended animation, waking only briefly to steer. 10 years later, a Russian schoolteacher turned rocket scientist named Konstantin Tsiolkovsky went further. Tsiolkovsky is one of the true founding minds of spaceflight, the man who worked out the basic mathematics of rocket propulsion decades before anyone had built one. In 1928, he described something much closer to what we now mean by a generation ship, a self-sufficient vessel he called a Noah's Ark, its crew fully awake for a journey lasting thousands of years, changing and adapting the entire way. Neither man was imagining a faster engine. They were imagining a slower, more patient answer to the same problem. If the ship cannot outrun the distance, the ship has to outlast it instead. That single shift in thinking removes something important from the equation. A generation ship doesn't need physics we don't already understand. No faster than light travel, which remains, and will likely always remain, in the territory of speculation. No exotic energy source that exists only inside an equation. It needs propulsion we already have in early form. Life support we already have in early form. And time. A generation ship, in other words, is not a technological fantasy. It's an endurance problem, and endurance problems get answered by arithmetic, not invention. The arithmetic itself starts unforgiving. Our nearest stellar neighbor, Proxima Centauri, sits 4.24 light-years from Earth. Light takes just over 4 years to cross that gap. Nothing built by human hands has ever come close to matching that speed. The fastest sustained velocity any spacecraft has ever achieved is a small fraction of 1% of light speed, and at that pace, the crossing would take more than 6,000 years. Turn that number around, and it gets stranger. 6,000 years ago, writing had barely been invented anywhere on Earth. The pyramids at Giza did not yet exist. Every civilization, every language, every human institution alive today was built inside a shorter stretch of time than the one this single voyage, one way, would require. That is the real timescale a generation ship has to survive. Not months, not years, longer than recorded history itself. And here's the part most people picture wrong. Its greatest enemy across that span was never a meteor, or an engine failure, or a hull breach, though each of those stays a real threat the whole way. Its greatest enemy is entropy, working on everything at once, on the metal, on the air, on memory, on the will of whoever happens to be alive inside it, in whatever century they happen to be born into. A dead ship drifts at exactly the same speed as a living one. Momentum, once you have it, is free in the vacuum of space. What has never once been free in the entire history of engineering is keeping something complicated alive without a single hand from outside ever reaching in to help. Nobody has ever built anything meant to run that long, completely alone. But something close was attempted once, on a much smaller scale, right here on Earth. 8 people sealed a door behind them, meaning to prove a closed world could sustain itself. Within 18 months, the air itself started to turn on them. The date on the door read September 26, 1991. 8 people stood inside a 3-acre world of glass and steel in the Arizona desert, and behind them, the seal closed for 2 full years. Biosphere 2 was not built to answer a small question. Inside its glass skin were 5 miniature biomes: a rainforest, a coral reef ocean, a mangrove wetland, a savanna, a fog desert, alongside farmland meant to feed the crew, and the sealed habitat where they slept. It was, at the time, the most ambitious attempt ever made to build a working miniature of Earth's own life support system. Closed, self-sufficient. In simple terms, it was the closest thing humanity has ever built to a generation ship. It nearly failed within the first year and a half. The oxygen began falling almost immediately after the door sealed, and it did not stop falling. Over 16 months, the concentration dropped from a normal 21% down to roughly 14%. Picture what that number actually feels like. 14% oxygen is close to what a person breathes standing on a mountain more than 15,000 feet high. Inside the dome, the crew grew tired for no obvious reason. Their thinking slowed. Some struggled to sleep through the night, and for months, nobody inside the glass, or outside it, could explain where the air was going. The first theory seemed reasonable, and it was wrong. Soil microbes in the biomes were consuming oxygen and releasing carbon dioxide faster than the young, still-growing plants could process it back into breathable air. That much was expected. What nobody expected was that the carbon dioxide wasn't building up in the air either. It was vanishing too, quietly, into something nobody had thought to watch. 2 scientists, Wallace Broecker and Jeffrey Severinghaus, finally traced it using isotope analysis, and the answer turned out to be almost embarrassingly ordinary: concrete. The structure's interior walls were built from concrete, and concrete contains calcium hydroxide, a compound that reacts with carbon dioxide and locks it into solid rock. A wall was never supposed to be part of the life support system. It was structure, not chemistry. But inside a truly sealed world, there's no such thing as an inert surface. Everything becomes a participant in the atmosphere, whether it was designed to be or not. Later analysis found the concrete had carbonated roughly 10 times deeper than concrete normally exposed to open air. because the interior atmosphere was so saturated with the gas trying to escape. Oxygen eaten by the soil. Carbon dioxide eaten by the walls. Nothing ever given back. By January of 1993, outside oxygen had to be pumped in to protect the crew. The experiment built to prove a sealed system could sustain itself needed an outside rescue within its first 18 months, just to keep its own people breathing safely. A system that requires resupply to function isn't, by definition, closed. Sit with that for a second, because Biosphere 2 was 3 acres, 8 people, 2 years, and it still managed to surprise its own designers with a failure mode nobody had modeled in advance, hiding in plain sight, inside the walls themselves. A real generation ship isn't 3 acres. It might need to sustain tens of thousands of people. It isn't 2 years. It might need to hold for centuries, with no door that opens, no truck bringing oxygen from outside, no team of geochemists on call to solve a mystery before it becomes an emergency. Biosphere 2 proved something valuable, just not what its designers had hoped to prove. It showed exactly how many invisible variables live inside a truly sealed world, and how fast even a brilliant, well-funded attempt at self-sufficiency can run into a mechanism nobody thought to shield against, because nobody thought to look at the walls. The crew who lived through it emerged in September of 1993, blinking into open air they hadn't tasted in 2 years, having learned something no simulation could have taught them any faster. Air isn't a resource you simply store and seal in. It's a live process, running every second, and something in that process will always be trying to slip away from you, often somewhere you weren't watching. 400 kilometers above the Arizona desert, where Biosphere 2 sits empty now, a much smaller machine is doing the same job, quietly, and it has never fully solved the problem either. The International Space Station's life support system, engineers call it ECLIS, is the most advanced closed-loop air and water hardware humanity has ever operated. Here's how the oxygen actually gets made. Electricity from the station's solar panels runs through water, splitting it into oxygen and hydrogen, a process called electrolysis. The oxygen goes to the crew. The hydrogen, in the system's original design, simply vented out into space and was gone for good. Think about what that means, stretched out over years. Every bit of hydrogen lost is water that has to be replaced from somewhere, and in low Earth orbit, somewhere means a resupply capsule launched from the ground. NASA has spent decades closing that gap. Today, the station's water recovery system reclaims roughly 98% of the water aboard, filtering and distilling sweat, breath moisture, even urine, back into water clean enough to drink. Out of every 100 pounds of water on the station, only about 2 pounds are ever truly lost. It's a genuinely extraordinary piece of engineering. It is still not a closed loop. That last 2% has to come from Earth, forever, for as long as the station keeps flying. The oxygen side has an even harder sealing built into the chemistry itself. A device called a Sabatier reactor takes the carbon dioxide the crew breathes out, combines it with hydrogen, and produces water and methane. Some of that oxygen gets recovered back into the loop, but methane carries hydrogen away with it when it's vented, and that loss sets a hard limit. Even in the best case, this process can only ever recover about 54% of the oxygen, not because the engineering is bad, because the reaction itself won't give any more back. Even NASA's most advanced closed-loop system, running today, cannot fully close its own loop without technology that doesn't exist yet. There's a kind of humility in that number worth sitting with. Some of the smartest engineers alive have spent decades chasing the last 2%, the last bit of hydrogen, the last sliver of oxygen slipping out of the system, and the chemistry itself keeps saying no, not yet. Maybe not ever, without an idea nobody has had. Now hold that number next to what a generation ship actually needs. The ISS supports 3 to 7 astronauts for missions lasting 6 months to a year, with cargo ships arriving multiple times annually, carrying fresh filters, spare pumps, new water. A generation ship would need to support a population possibly in the tens of thousands for centuries, with a resupply rate of exactly 0. Every leak the ISS patches with a part flown up from Earth, a generation ship has to patch with something built or fabricated entirely from what it already carries, forever. Every filter the ISS swaps out on a schedule, a generation ship has to manufacture from its own onboard resources, without a single new atom of raw material ever crossing the hull again after the day it departs. This isn't a hypothetical gap. NASA's own engineers describe the resupply requirement plainly as an ordinary fact of the mission, because launching fresh air and water and hardware to orbit is expensive and constant, and nobody's pretending otherwise. Take that supply chain away completely, permanently, and every one of those hard-won efficiency numbers quietly stops being an achievement. It becomes a countdown. Somewhere on a real generation ship, 3 centuries in, an engineer checks a gauge she's checked 10,000 times before. The number is fine. It's always fine, until the morning it isn't, and there's no cargo ship coming to fix whatever goes wrong that day. The machine that keeps a crew breathing is only the beginning of the problem. The moment the ship leaves the shelter of Earth's magnetic field completely behind, a threat begins working on its passengers that no filter, no seal, no clever recycling can ever fully stop. Somewhere aboard, a woman checks rows of wheat growing under banks of pink-tinted light, the way her mother checked them, and her mother before that. The wheat doesn't know it's traveling, it just grows, the way wheat always has, toward whatever light it's given. Air and water can be recycled with clever enough engineering. Food is different. Food has to be grown, continuously, forever, by something alive, and every calorie eaten aboard a generation ship has to come from somewhere the ship carries with it. NASA has been quietly working on this exact problem since the 1980s, at Kennedy Space Center, in a facility called the Biomass Production Chamber, the first controlled environment vertical farm built in the United States. Researchers there spent years answering one specific question: can you actually grow enough food to matter inside a fully sealed environment using only artificial light and recycled water? The answer turned out to be yes, with a catch. Plants grown this way, under the right conditions, grow at essentially the same rate as they would in an open field. The catch is space and power, and the sheer scale required to feed real people real calories, day after day, for a lifetime. The numbers give you a sense of what enough actually means. Space agriculture researchers estimate that intensive vertical farming, stacked hydroponic systems, tightly controlled light and nutrients could provide the bulk of one person's diet using around 13 square meters of growing area. That's not the whole diet. Getting close to full self-sufficiency, according to older NASA station design studies from the 1970s, pushes that number towards 61 square meters of agricultural space per person, once you're accounting for the full range of crops a real diet requires, not just quick-growing greens. Feeding one person, completely, indefinitely, without a single supply run from Earth, takes roughly the floor space of a small house. Now multiply that by 20 or 40,000 people, the population range this exploration has already suggested a real generation ship would need for genetic survival, and food production alone becomes one of the largest single systems the ship has to carry. and growing the food is only half the loop. Every plant a person eats takes nutrients out of the soil or the water, and unless those nutrients come back around through composted waste, recycled water, carefully balanced chemistry, the system slowly starves itself from the inside, exactly the way Biosphere 2's atmosphere quietly starved itself through a wall nobody thought to watch. NASA's own research into what they call bioregenerative life support has spent decades mapping this exact cycle, growing crops that produce oxygen and food while recycling wastewater and carbon dioxide at the same time. 3 problems solved by the same living system. It works. It has worked in test chambers on Earth for months at a time. Nobody has ever run it, uninterrupted, at full scale, for centuries. The woman checking her wheat doesn't think about any of this while she works. She thinks about whether this row looks a little pale compared to last week's, whether the light banks need adjusting, whether dinner will taste like it always does. The math behind her morning is enormous. Her actual task is small, ordinary, and has to be done exactly right, every single day, for as long as the ship exists. Air, water, food. 3 systems that have to run without failure, forever, invisible until the day one of them doesn't. But none of it matters if the ship itself starts coming apart from a single point of failure nobody caught in time. A child is born aboard the ship in year 140, in a room designed to feel safe, warm, ordinary. Nobody tells her that from the moment she takes her first breath, her body is absorbing something that never once touched her parents at anywhere near this rate back on Earth. She will never feel it happening. That's what makes it different from almost every other danger on this voyage. It doesn't announce itself. Air can be recycled, filtered, rebuilt with enough clever engineering. Radiation can't. It simply arrives, continuously, and once you're far enough from home, there is no filter that removes it completely. Earth is shielded twice over, and almost nobody thinks about either layer until it's gone. The planet's magnetic field, generated deep in its molten core, reaches out into space as the magnetosphere, deflecting most of the charged particles thrown off by the sun. Further out, the sun's own magnetic field inflates a vast bubble around the whole solar system called the heliosphere, which blocks much of the harsher radiation arriving from outside it entirely, the galactic cosmic rays born in distant supernova explosions. Together, these 2 shields are the reason an astronaut aboard the ISS, still safely inside the magnetosphere, absorbs an average of about 150 millisieverts of radiation a year. For comparison, the public safety limit on Earth's surface is 1 millisievert a year, and a single chest X-ray delivers roughly 0.1. An ISS astronaut is already living at a dose no ordinary person on the ground ever would. Now take that same astronaut and move her past both shields entirely, into true interstellar space. Out there, exposure to galactic cosmic rays runs at roughly 500 millisieverts a year, more than 3 times the ISS rate, and that number holds for every single year of a multi-century voyage. No good years to offset the bad ones. Leaving the solar system doesn't just mean losing a convenience. It means losing the 2 layers of shielding that make survivable long-duration spaceflight possible at all. So build a thicker wall, you might think. Engineers have studied exactly that, and the numbers aren't encouraging. Roughly 7.5 centimeters of aluminum shielding is the current recommendation around any habitable area of a long-duration spacecraft. That's already a heavy engineering commitment. But galactic cosmic rays are strange particles, so energetic that shielding against them doesn't behave the way shielding against an ordinary X-ray does. Even 30 centimeters of aluminum, 4 times that recommendation, only cuts the dose by 25 to 40%. Past a certain thickness, the incoming particles start colliding with the shielding material itself, spraying new radiation into the very room the wall was supposed to protect. You can't just build your way out of this one. Past a certain point, the wall starts working against you. Here's the part that has to be said plainly, without softening it more than the truth allows. A generation ship's crew, and every child born aboard across centuries, would absorb cumulative radiation exposure far beyond anything any human population in history has experienced, for their entire lives, generation after generation. The known effects include elevated cancer risk and documented impacts on the nervous system. What we genuinely don't know, what nobody can know yet, is what that dose does across multiple successive generations, to the reproductive cells, to a child developing inside a mother who has never once stood beneath an unfiltered sky. Nobody disagrees about this because the science is unsettled. Nobody knows because the only experiment that could answer it has never been run, and by its nature, could never safely be run on purpose. The girl in the warm room grows up anyway. She learns her letters, skins her knee, falls asleep to the low hum of machines built to keep her alive. The radiation keeps arriving the entire time, quiet, invisible, patient. It has nowhere else to be. Radiation works on bodies slowly, over years and centuries. But there is another kind of decay working on the ship itself, on the metal, the welds, the thousands of small joints holding a pressurized hull together against the vacuum just outside it. A hull is not really a wall. Think of it more like a held breath. On one side, a livable pressure, warm air, people going about ordinary lives. On the other, a vacuum that would kill everyone inside within seconds if that breath were ever let go. And it has to be held without a single moment of relief for as long as the mission lasts. We already have real, measured data on how metal structures age in space, and the number is sobering against the timescale a generation ship needs. The International Space Station's modules were engineered for a 15-year structural life, doubled through an engineering safety margin to roughly 30. The first hardware launched in 1998. By NASA's own analysis, the structure was already nearing the edge of that lifespan by 2013, and every year since has required fresh engineering study just to certify the primary structure is still safe to keep pressurized. Humanity's most sophisticated orbital structure, in other words, was never built to last even a single century, let alone several. Here's what actually wears a spacecraft down. Not one dramatic event. Thousands of small, ordinary ones, stacked on top of each other. Every orbit around Earth bakes one side of the station in direct sunlight and freezes the other in shadow, and that constant heating and cooling, thousands of times a year, stresses the metal joints and welds at a microscopic level nobody can see happening. Every docking, every undocking, sends a small mechanical shock through the frame. None of it is dangerous on its own. But multiply a tiny, harmless stress by tens of thousands of repetitions across decades, and you get material fatigue, the same slow process that eventually cracks a bridge or grounds an aircraft that's flown too many cycles. A generation ship has none of the ISS's advantages here. The ISS gets inspected regularly by visiting crews, resupplied with spare structural parts, watched constantly by engineers on the ground who can catch a developing problem years before it turns dangerous. A ship, 3 centuries into its voyage, has none of that. Whatever fatigue is quietly building in a structural joint has to be caught and fixed entirely by whoever happens to be aboard, using only what the original crew brought with them or whatever the ship's own manufacturing systems can produce from scratch, out of raw material that will never be replenished. Then there's the debris. Even a tiny grain of interstellar dust carries enormous kinetic energy at the speeds a generation ship would be traveling. Spacecraft today use something called a Whipple shield, several thin layers spaced apart, so an incoming particle shatters against the outer layer and disperses into a harmless cloud before it can punch through to the pressurized hull behind it. It works well at the comparatively gentle speeds common in Earth orbit. Nobody has ever tested how that same shielding holds up against sustained impacts at a real fraction of light speed over centuries, because nothing built by human hands has ever traveled that fast for that long. There's no way to run the test in advance. The first real data point would be the voyage itself. That's the honest shape of the hull problem. Every material ever engineered for spaceflight has been tested and proven across years, sometimes a few decades. A generation ship asks that same category of material to hold, silently, invisibly, without inspection or resupply, for a length of time nothing has ever actually been asked to endure. Redundancy helps. Multiple independent structural sections help. But redundancy carries mass, and mass is the one thing a ship crossing light years can never simply add more of. Hold pressure, keep moving. That's the hull's entire job description. Getting up to speed and stopping again at the far end turns out to be a separate and much uglier problem. In October of 1968, a technician at a manufacturing plant in Downey, California, was lifting an oxygen tank out of a spacecraft for a routine modification, and it slipped, fell about 2 inches, landed hard enough to jar an internal fill line, just slightly, in a way nobody could see from the outside. The tank looked fine. It was inspected, and it looked fine. It was cleared, reinstalled, and eventually bolted into the service module of a mission called Apollo 13. Nobody involved was careless. That's the part worth sitting with before anything else. Every step in this story was handled by trained, careful people, following real procedures, and the mistake still slipped through 5 separate checkpoints in sequence, each one reasonable on its own, each one missing exactly the one thing that would have stopped everything downstream. Here's how the chain actually ran. Back in 1965, engineers had upgraded the tank's internal heaters to run on a higher voltage, 65 volts instead of 28, to match newer ground support equipment. The thermostatic switches, meant to protect the heaters, were never updated to match. Nobody caught the mismatch. Then came the drop in 1968, damaging a line nobody could inspect without disassembling the tank, so nobody did. Then, during a final ground test before launch, engineers ran the heaters for hours longer than intended to boil off leftover oxygen, and the outdated thermostat, rated for the old lower voltage, welded itself shut instead of shutting off. Temperatures inside the tank spiked past 1,000 degrees Fahrenheit, quietly cooking the Teflon insulation off the internal wiring, invisible from the outside, invisible on every gauge anyone was watching. The tank went up anyway, on April 11, 1970, carrying exposed wire sitting in pure oxygen, a small bomb nobody knew they'd built. 2 days into the mission, an astronaut flipped a routine switch to stir the tank's contents. The exposed wire sparked. The spark caught the surrounding insulation. Pressure inside the sealed tank climbed until the tank ruptured, blowing an entire panel off the side of the spacecraft and damaging the second, backup oxygen tank in the process, the one system that was supposed to keep the crew alive if the first one ever failed. Flight director Gene Kranz would later describe what happened next in mission control in exactly the language engineers use for this pattern: one failure, propagating into many, a cascade, each system's collapse taking out the next one down the line. The crew survived. Barely, and only through a genuinely heroic improvisation, using the lunar module as an emergency lifeboat. But notice what actually caused the crisis. Not one dramatic failure, 5 small, individually forgivable oversights, made years apart, by different people, none of whom ever saw the full chain they were building, until oxygen was venting into space, 200,000 miles from home. A generation ship multiplies this exact risk by every year it operates, every system it carries, every small modification made by an engineer who will never meet the engineer 3 generations later who inherits the consequences. Redundancy helps, genuinely. A backup oxygen tank helped Apollo 13's crew survive. But redundancy only works if the backup system stays truly independent of the one that failed. Physically, electrically, structurally, and Apollo 13's own disaster proved exactly how easily that independence quietly erodes, one small shared oversight at a time, until the day the primary system fails and drags its backup down with it. In a small office in London in the early 1970s, a dozen volunteer engineers sat down with a strange kind of homework. Design a ship that could reach another star within a human lifetime, using nothing but physics they were confident actually worked. No shortcuts, no science fiction, just numbers that had to close. Every propulsion concept ever seriously studied for interstellar flight runs into the same wall almost immediately, and the wall isn't speed, it's fuel. Chemical rockets, the kind that have carried every human being who's ever left Earth, are so inefficient at these distances that the numbers stop being useful. Reaching even a small fraction of light speed with a chemical engine would take more fuel than the ship could ever physically carry, several times over. So serious studies have looked past chemical propulsion entirely towards something closer to a controlled explosion. The fuel doesn't burn, it detonates. That London team called their project Daedalus, and it remains the most detailed engineering study of its kind. Led by Alan Bond, they aimed for Barnard's star, 5.9 light-years away. Their design, a 2-stage vehicle with a total mass of 54,000 tons, of which 50,000 tons, more than 90% of the entire ship, was fusion fuel. The vehicle would detonate small pellets of deuterium and helium-3 at a rate of 250 times every second, accelerating for roughly 4 years until it reached close to 12% of light speed. At that velocity, the one-way trip would take about 50 years. 90% fuel for one modest science payload. Sit with that ratio for a second. Now imagine scaling it up, not for a probe, but for a ship carrying tens of thousands of people, their food systems, their water, their manufacturing capacity, everything a civilization actually needs to keep existing. The fuel required scales with the mass being moved, and a generation ship's mass dwarfs anything the Daedalus team ever proposed launching. And here's the detail that matters most, the one most people miss entirely. Daedalus was never designed to stop. It was a flyby by design, meant to streak past its target at enormous speed, gather what data it could in one brief pass, and keep going forever afterward into the dark. There was no deceleration stage, because slowing that much mass from over 1/10 of light speed would have roughly doubled the fuel load for a payoff on an unmanned probe that wasn't worth the mass penalty. It wasn't until decades later, in a follow-up study called Project Icarus, that engineers finally built deceleration back into the design, and even then, only by cutting the payload mass dramatically. That single choice tells you where the real difficulty sits. Getting up to speed is, relatively, the easier half, because an unmanned probe can afford to just keep going once it's launched. A generation ship can't do that. It's carrying people who are going somewhere specific, and arriving means actually stopping, not streaking past at a meaningful fraction of light speed. Stopping means carrying, and successfully firing, a second enormous fuel load, decades or centuries into the voyage, using engines that have sat largely dormant and aging the entire time, with no ground crew to inspect them, and absolutely no chance for a dress rehearsal. A ship that can get up to speed, but can't reliably slow back down, isn't a generation ship at all. It's a very well-engineered way of missing your destination forever, permanently, at a significant fraction of the speed of light. Even a perfectly designed hull, moving at exactly the right speed, arriving exactly on schedule, means nothing if there's no one left aboard who actually understands how to run the ship by the time it gets there. Ask NASA's Voyager project manager, Susie Dodd, what it's actually like to talk to the most distant object humanity has ever built, and she describes it almost like writing a letter to someone overseas. If I send a command and say, "Good morning, Voyager," at 8 in the morning on a Monday, she's explained, I get its response back Wednesday morning, at roughly the same time. This isn't a metaphor. This November, Voyager 1 will cross a real, specific threshold, one light day from Earth, a distance so vast that a radio signal traveling at the fastest speed the universe allows takes a full 24 hours just to arrive, and another full day for a reply to make its way back. A single exchange, hello and response, takes 2 entire days. Not because anyone is slow, because that's simply how long light takes to cross that much empty space, and light is as fast as anything gets. It helps to build up to that number gradually, because it's easy to say and hard to actually feel. When Apollo astronauts stood on the moon and spoke to mission control, there was a small, strange gap in the conversation, about a second and a half, the actual time light needs to cross the 238,000 miles to the moon and back. Barely noticeable, mostly just a slight formality in how people took turns speaking. Reach out to Mars instead, and that gap stretches to as long as 20 minutes each way. Long enough that a rover on the Martian surface can't be joysticked in real time, has to be given instructions, and left to carry them out alone, because by the time trouble shows up on a screen back on Earth, it's already ancient history. Now reach out to Voyager 1, still inside our own solar neighborhood in cosmic terms, barely a rounding error past it, and the gap becomes a full day, each direction, 2 days round trip, for a single yes or no. A generation ship traveling toward Proxima Centauri would eventually leave that gap so far behind that the comparison stops being useful entirely. At 424 light-years out, a message sent home wouldn't take hours or days. It would take years, just one way, arriving at Earth long after whoever sent it had likely already grown old or died, waiting for an answer that would arrive on its own schedule regardless. Somewhere past a certain point in the voyage, the very idea of asking Earth for help stops making practical sense at all. Not because nobody would answer, because the answer would arrive so many years later that the question it was responding to would belong to a different generation entirely, asked by people no longer alive to hear it answered. Every engineer aboard a real generation ship would understand this instinctively, the way Voyager's own team already has to. You don't design a system that depends on a timely answer from home, because there will never be one. Every decision, every emergency, every judgment call has to be made entirely by whoever is aboard, in the moment, with whatever knowledge and equipment already exists inside the hull. Earth becomes, for practical purposes, a place that used to matter operationally and no longer does. This is the quiet, specific way Distance actually ends a relationship with home, not with a door slamming shut, with replies that keep arriving, faithfully, correctly, from further and further in the past, until eventually, the delay itself becomes the entire relationship, longer than the conversation ever was. A young engineer kneels beside a reactor housing in year 210, listening. Her mentor taught her to listen for this exact sound, a faint irregularity in the hum, the kind of thing that means trouble is coming before any gauge would show it. But her mentor learned that skill secondhand too, rushed, during a year when the ship had lost 2 senior engineers to accident within months of each other, and there hadn't been time to teach it properly. She listens now, unsure if she's hearing the warning sign or just hearing what she was told to expect. Every generation ship design begins with a crew that is, by definition, extraordinary. Volunteers, screened, trained for years, specialists who already understand the machine they're about to spend their lives inside. That's the crew every mission plan assumes. It's also a crew that exists for exactly 1 generation. Their children didn't apply for this life, weren't screened for aptitude, didn't choose their profession. They're simply born into whatever role the ship's survival requires of them, and everything they know about keeping that ship alive has to come from somewhere, taught by someone who was themselves taught by someone, in an unbroken chain reaching back to that original trained crew. A generation ship isn't just a physical structure, it's also an educational chain, and chains are only as strong as their weakest link. Researchers who study organizations here on Earth have spent decades looking at a much smaller, much lower stakes version of exactly this problem. They draw a consistent line between 2 kinds of knowledge. Explicit knowledge is the kind you can write down, a manual, a checklist, a diagram, something you can simply hand to the next person. Tacit knowledge is different. It's the accumulated instinct, judgment, and hands-on skill a person only develops through years of direct practice, the kind of knowledge an expert often can't fully explain, even when they try. And the research keeps finding the same uncomfortable thing. Most of what a senior expert actually knows never makes it into the official documentation. It only transfers through direct mentorship, side by side, over time, or it doesn't transfer at all. Now picture that same chief engineer, 3 centuries into the voyage. The manuals will survive. Manuals are explicit knowledge, written down, backed up, safe. But a manual doesn't tell you what a slightly wrong sound means before a bearing fails. It doesn't carry the felt judgment of which repair to prioritize when 3 systems degrade at once. That kind of knowledge needs a mentor standing right there, generation after generation, without a single broken link. Even here on Earth, in ordinary companies with no threat to survival attached, organizations report real, measurable knowledge loss whenever experienced staff leave faster than new staff can be properly taught. A generation ship takes that same fragile process and raises the stakes past anything a company on Earth ever faces. There's no outside hiring pool, no rival firm down the street to poach an expert from if the ship's own apprenticeship chain breaks, even once. If the 4th generation's engineers were taught by mentors who were themselves only half-trained because the 3rd generation lost too many specialists too fast, that gap doesn't stay flat. It compounds, quietly, the same way fatigue compounds in a hull, until something finally fails, and nobody fully understands why or how to fix it. Most people picture a generation ship failing with a bang, a hull breach, a dramatic accident. Historically, when complex systems fail after decades of quiet operation, they tend to fail exactly like the young engineer kneeling by the reactor, uncertain whether she's hearing a warning or just an echo of something she was told to listen for. somewhere between what one generation actually knew and what the next one was actually taught. There's a period in the history of human isolation research that shows this same pattern with unusual clarity. It's worth pausing on before returning to the ship itself. June 3rd, 2010. 6 men walked into a sealed facility on the outskirts of Moscow, and behind them, a door closed that would not open again for 520 days. 3 Russians, 2 Europeans, 1 Chinese. They shook hands with the engineers who'd built the place, said their goodbyes to daylight, and stepped inside. The facility itself was small, about 550 cubic meters, roughly the size of a modest house, split into individual sleeping quarters, barely large enough to lie down in, a shared kitchen, a small greenhouse module, and almost nothing else. This was Mars 500, the most complete simulation of a long-duration interplanetary mission ever attempted, and its entire purpose was to answer one narrow, practical question: what does real isolation actually do to a healthy human mind and body over more than a year and a half? There was no window, no fresh air. Meals came from stores calculated down to the calorie, months before anyone had sealed the door. For 520 days, the only sky these 6 men saw was a photograph someone had taped to a wall. And even that, after a while, some of them stopped looking at. The results, once researchers finished analyzing them, weren't encouraging. Wrist-worn sensors tracked the crew's sleep through the whole mission, and the data showed something getting worse as the months wore on. Reduced sleep efficiency, longer stretches lying awake before finally drifting off, both trends sharpening in the final weeks. Weekly mood assessments turned up a pattern researchers ended up calling the third quarter phenomenon, a dip in morale and motivation that didn't hit at the start, when everything was still new, and didn't hit near the end, when the finish line was close enough to see. It hit in the long, undifferentiated middle, when one day had stopped feeling any different from the last. Muscle strength testing found measurable decline in the crew's legs over the course of the isolation too, even with a structured exercise routine built into every week. Picture what that actually means. These were 6 healthy, carefully screened, highly motivated volunteers, chosen specifically for psychological resilience, sealed inside a facility on the surface of Earth, with a known and finite end date circled 520 days out that they could count down toward, day by day, on a calendar taped to a wall. And even under those relatively gentle conditions, isolation still measurably wore down their sleep, their mood, their strength. Now hold that finding against what a generation ship actually asks for. 520 days is a year and a half. A generation ship's voyage runs for centuries. There's no finish line 600 days out that anyone aboard can count toward, because nobody alive on the ship will live to see the mission's actual end. No date circled on a calendar to hold on to through the hardest stretch. Just the plain fact that this is simply what life is, indefinitely, for every single person born aboard, generation stacked on generation. Mars 500 tested the cost of isolation with an endpoint clearly in sight. A generation ship removes the endpoint entirely for everyone born after the very first crew. This remains, in the most literal sense, the closest real data humanity has ever gathered on sustained isolation, and it only reaches a year and a half into a problem that would need to hold for hundreds of years. What happens after that, no experiment has ever run long enough to say. There's a second, quieter shift waiting underneath this one though, and it has nothing to do with how long the isolation lasts. It has everything to do with whether anyone chose it in the first place. In October of 2018, At a research station on King George Island, off the coast of Antarctica, a 61-year-old welder named Oleg Beloguzov was stabbed in the chest by a colleague he had worked alongside for more than 6 months. The station, called Bellingshausen, sat completely isolated through the Antarctic winter. 12 researchers, no way in or out until the season turned. The head of the Russian Antarctic expedition later told reporters, in something close to genuine disbelief, that nothing like this had ever happened at one of their stations before. The attacker, a 64-year-old scientist named Sergei Savitsky, had shown no history of violence before that winter. Investigators pointed to what Russian officials described simply as tensions in a confined space. The accumulated weight of month after month spent with the same small group of people. No outside contact, no way to simply walk away from a disagreement and cool off somewhere else. Beloguzov survived, evacuated to a hospital in Chile. He later dropped the charges. This isn't an isolated story, and that's precisely the point worth sitting with. Antarctic research stations have documented a real, recurring pattern researchers now call the third quarter phenomenon, the same effect Mars 500 measured in its simulated crew. Morale and cohesion holding reasonably well in the first weeks of isolation, holding again near the very end when a known departure date comes into view, and eroding hardest in the long, undifferentiated middle, when the season feels endless and the people around you have become the entire world. A widely repeated, if harder to verify, story from a Soviet station in 1959 holds that a researcher there killed a colleague over a chess match, a story unconfirmed in its exact details, but taken seriously enough that chess was reportedly banned at Soviet Antarctic stations afterward. More recent, better documented cases keep surfacing too. A South African base reported an assault and death threats among its overwintering team in 2025, after less than a month of tension over a scheduling dispute. Officials in that case noted candidly that even careful pre-departure psychological screening doesn't reliably predict who will struggle once the isolation actually sets in. Every one of these stations had something a generation ship's population would not. A departure date, months or a year out, circled on a calendar somewhere. A resupply ship that would eventually come. A rescue that remained, however difficult, at least theoretically possible if things went badly wrong. None of these winters lasted more than about a year. None of these crews numbered more than a few dozen people. And even under those relatively contained conditions, isolation still occasionally broke something in someone, badly enough to end in violence, on a continent still technically part of the same planet everyone involved had been born on. A generation ship compounds every one of those pressures simultaneously, for a population in the tens of thousands, sustained not for one winter, but for centuries, with no season ever turning, no ship ever arriving, no possibility of transfer to another posting if a conflict between two people, or two families, or two factions ever hardens into something that can't simply be waited out. Every ethical idea humanity has ever built around consent starts from one basic condition: the person affected exists first and gets asked, or at the very least, is free to leave second. A generation ship breaks that condition immediately and permanently for every single person born after the airlock first seals shut. The first generation aboard would almost certainly be volunteers. Adults, screened, fully informed, choosing this mission with a clear-eyed sense of what they were giving up. Whatever else you say about that choice, it is, at minimum, a choice. Their children are a different matter entirely. A child born into the ship's second generation didn't apply for any of this, didn't consent, didn't choose a life sealed inside a hull, breathing recycled air, with no possibility of ever setting foot on open ground. They were simply born into it, the way anyone is born into their circumstances, except with one difference that changes everything. There's no leaving, no other neighborhood, no other country, no plane ticket home, ever. The ship is the entire world for their entire life, and somebody else chose that for them before they existed to have an opinion about it. Imagine, for a moment, a teenager aboard, somewhere around year 80, asking her grandmother the obvious question: why did they leave? Her grandmother wasn't born yet when the decision was made either. Neither was her mother. The answer, by now, has passed through so many hands that it sounds less like a reason and more like a story everyone has simply agreed to keep telling. This isn't a concern only casual observers raise. It's become real academic territory, researchers writing specifically about what's come to be called worldship ethics. The obligations owed to a generation ship's crew use a particular word for this population, the shipborn, meaning everyone born and raised entirely aboard, who will also die aboard, having never known anything else. Published philosophical work on the question argues that avoiding real exploitation of the shipborn requires guaranteeing certain freedoms across every generation, not just the first. The freedom to choose your own vocation rather than simply inheriting an assigned role. Freedom over your own reproductive choices, rather than having childbearing treated as a mission requirement handed down like a duty roster. Think about what that actually demands, generation after generation. The mission's entire survival depends on people continuing to have children in specific enough numbers at a specific enough rate to keep the population from quietly collapsing. That need doesn't go away just because a given generation might, understandably, start to wonder why they owe their own children a life they themselves never chose. A generation ship's survival isn't only a matter of machinery holding together. It requires an unbroken, multi-century agreement among people who never agreed to anything, to keep participating in a mission decided for them long before they were born. This is where purpose turns into a maintenance problem, in the same category as the air and the hull, except harder, because purpose can't be manufactured on board from raw material. It has to be actively, continuously reinforced, culturally, generation after generation, or it quietly erodes. A crew who still feel the original mission's meaning are a very different population from one that's come to see the ship less as a noble voyage and more as a sentence being served on behalf of ancestors who aren't around anymore to explain themselves. And even if every generation somehow keeps that sense of purpose alive, there's a colder, more mathematical problem waiting just beneath the philosophical one. It has nothing to do with meaning at all. It has to do with a number, and the number is bigger than almost anyone guesses. A child aboard the ship, 6 generations in, uses a word for the reactor room that her ancestors, the ones who actually boarded on departure day, would not recognize at all. Nobody taught it to her deliberately. It simply grew, the way a plant grows toward whatever light happens to be available, shaped by 5 generations of children, mishearing, simplifying, and reinventing the words the generation before them used. Language is not a fixed possession. It's a living process, rebuilt from scratch, inside every single child who ever learns to speak. Linguists have studied exactly how that rebuilding works, generation after generation, and the finding is consistent enough to be treated as close to a law. Each child doesn't simply copy the language spoken around them. They reconstruct their own internal grammar and vocabulary based on what they hear, and that reconstruction is never perfect. Small shifts creep in every single time, pronunciations drifting, meanings sliding, new words getting invented or borrowed to fill gaps nobody planned for. No individual shift is significant. Stacked across generations, though, those shifts compound the same way structural fatigue compounds in a hull. Historical linguists have measured roughly how long that compounding takes before it becomes irreversible. Studying real language families with documented histories, they find that after around 1,000 years, a language and its own ancestral form are no longer mutually intelligible. Someone speaking the descendant language couldn't understand someone speaking the original, even though one grew directly out of the other, with no single break in the chain, ever. The Romance languages, French, Spanish, Italian, Portuguese, Romanian, all descend from a shared form of Latin, and that divergence unfolded across roughly 2,000 years. The Germanic languages branched apart on a similar multi-century timescale. None of this required war or conquest or any dramatic rupture. It happened simply because each generation of children rebuilt the language slightly differently than the generation that taught them, and those tiny differences never stopped accumulating. Now place a generation ship's population inside that same slow current. 250 years, the working baseline this exploration has already used for a realistic voyage, is a quarter of the distance linguists generally cite before mutual intelligibility starts to break down entirely. It's easily enough time for real, noticeable drift, new slang, shifted pronunciation, technical vocabulary mutating as engineers explain machinery to apprentices who then explain it to their own apprentices, each retelling a small copy of a copy. A journal entry written by the ship's very first generation might already read, to the ship's fifth generation, the way a document from several centuries ago reads to us today. Recognizable, a little strange, requiring real effort to parse correctly. This matters for reasons well beyond nostalgia. Technical manuals, safety procedures, the entire explicit knowledge base this exploration has already discussed are all written in a specific version of a language, frozen at the moment of departure. If the spoken language keeps drifting, while the written manuals stay fixed, a gap slowly opens between what the ship's crew actually speaks and what its own critical documentation says, generation after generation, until eventually someone has to translate their own ship's founding technical library into whatever language they've since grown up speaking instead. Ask most people how many humans it would take to crew a generation ship, and they picture something like a submarine crew or a small research station. A few dozen maybe, 100 at most. The actual research says that guess is off by 2, sometimes 3, orders of magnitude, and the reason comes down to one word: genetics. One of the earliest formal estimates came from anthropologist John Moore at the University of Florida, who calculated that roughly 150 people could sustain a voyage lasting around 2,000 years, something like 200 generations. For years, that number floated around as something close to a working consensus. Then, in 2014, anthropologist Cameron Smith, working with a research group called Project Hyperion, ran the numbers again, using detailed population genetics modeling this time, and the story changed completely. Here's the simple version of what genetics actually does inside a small, closed population. Everyone carries 2 copies of most genes, one from each parent. Some of those copies carry harmful traits that only cause a problem if a person happens to inherit the same bad copy from both sides. In a large population, the odds of that happening are low because there are millions of unrelated people to draw from. Shrink the population down to a few hundred, related to each other through only a handful of founding ancestors, and those odds climb, generation after generation. Smith modeled exactly this, running the numbers out across 30 generations, feeding in real assumptions about mutation, migration, and chance. A starting population of 150, Moore's original number, loses roughly 80% of its genetic diversity in that time. Not a healthy population slowly adapting to space. A population sliding toward the same fate as a critically endangered species in a captive breeding program, watched over by geneticists, trying to keep a shrinking bloodline alive. Smith's conclusion: a genuinely safe founding population needs to be dramatically larger. A minimum of around 10,000 people, with 20 to 40,000 recommended as a real safety margin against disease, accidents, and the ordinary bad luck of small population demographics over centuries. 20 to 40,000 people isn't a crew. It's the population of an entire small city, sealed permanently inside one hull, expected to sustain itself, biologically, forever. It's worth being honest here, because the science doesn't fully agree yet, and that disagreement tells you something too. Not every study lands on Smith's larger figure. More recent modeling, using different methods and more permissive assumptions about acceptable risk, has calculated viable populations as low as roughly 100 people under certain narrow conditions. The range across the published literature is wide, mostly because the true answer depends on questions nobody has settled yet. How much genetic risk is a mission willing to accept? How is the population managed across generations? How bad does a single unlucky event get to be before the whole thing becomes unrecoverable? Even taking the most optimistic estimates seriously, the practical result barely changes. A generation ship built for genuine long-term genetic safety isn't a small, tight-knit crew. It's closer to a sealed nation, and every additional person added for genetic safety adds mass, adds air demand, adds food production requirements, stacking directly onto every engineering problem this whole exploration has already walked through. Genetic diversity on its own is only half the story, though. What actually happens, mechanically, inside a bloodline that's too small, generation after sealed generation, turns out to have already happened once or twice, right here on Earth, on islands far smaller than any ship. A Scottish soldier named William Glass stepped onto a volcanic island in the middle of the South Atlantic in 1817, built a home, and stayed. Tristan da Cunha, he called it, one of the most remote inhabited places on Earth, over 1,000 miles from the nearest port. He had no idea he was starting a genetics experiment that would still be studied, in detail, more than a century and a half later. For generations after Glass arrived, the island's population stayed almost completely isolated, marrying nearly always within the same small founding group. By the mid-20th century, geneticists studying the island's descendants found something striking. Retinitis pigmentosa, a rare, inherited condition that slowly causes blindness, affects roughly 1 in 6,000 people in the general British population. Among Tristan da Cunha's small, closely related community, the condition showed up far more often than that background rate, alongside an unusually high prevalence of hereditary asthma across the island's descendants, more than half the population carrying some form of it by the time researchers came to study the island properly. Neither disease appeared because the island was cursed or unlucky. They appeared because a small handful of founders happened to carry certain recessive genes, and generations of limited mixing gave those genes far more chances to pair up than they'd ever get in a larger population. Pitcairn Island tells a similar story from a completely different beginning. In 1789, 9 mutineers from the British ship Bounty, along with a small number of Tahitian companions, settled the isolated island, and the population that grew from them stayed genetically traceable back to that same handful of founders for generations. Their surnames still mark distinct family lines on the island today, a living record of exactly how few people it took to start the whole community. Now place a generation ship's population inside that exact same mechanism, stretched across a scale and duration far beyond anything Tristan da Cunha or Pitcairn ever experienced. A ship's population can't simply wait for a passing vessel to bring new settlers, the way isolated island communities on Earth occasionally could. There's no passing ship in interstellar space. Whatever genetic diversity leaves Earth with the initial crew is, for all practical purposes, the entire genetic diversity the mission will ever have, unless the ship is deliberately designed from the very start to manage that risk on purpose. Real proposals for how to do exactly that already exist in the published literature, and they're worth taking seriously rather than waving off as science fiction. Careful record-keeping of lineage to minimize close relative pairings, onboard storage of frozen sperm, eggs, or embryos, collected from a much wider, more diverse population before departure, to inject new diversity into the bloodline at intervals throughout the voyage without requiring anyone new to physically join the crew. These are proposed mitigations, not guarantees. Whether they'd actually work, sustained without error, for centuries, remains an open question nobody has ever had the chance to test at true generation ship scale. Even a population with perfectly managed genetics is still made up of individual people living individual lives, and it's worth pausing the numbers here, just for a moment, to remember what that actually looks like from the inside, for one person, in one ordinary year of a very long voyage. You wake up in a room with no window, and it has never once occurred to you that a room should have one. This is year 90 of the voyage. You are somewhere in the ship's third generation, and you did not choose this life any more than you chose your own face. The Project Hyperion Research Group, a real ongoing engineering study into generation ship design, uses roughly 250 years as a working baseline for a voyage like this. 250 years isn't an abstract span. It's about 3 full human lifetimes, laid end to end. You did not know Earth. Your parents only know it from stories, and their parents knew it from stories about stories, each retelling a little further from whatever it actually was. The only sky you've ever seen is a ceiling, engineered carefully enough that most days you forget it's a ceiling at all. The only ground you've ever stood on has an engine somewhere underneath it, and you've felt that engine's hum in your feet since before you could walk. You'll live your entire life aboard. You'll learn a trade, most likely one assigned by whatever the ship happens to need in your generation, not necessarily the one you'd have chosen freely, back on a world you'll never see. You might fall in love, the ordinary way people do, across a shared table in the mess hall, over some small joke repeated until it becomes the two of you. You might raise children of your own, grow old, breathing the same recycled air your grandparents breathed, that your own grandchildren will breathe long after you're gone. And here's the part that's easy to say and much harder to actually sit inside. You will die aboard this ship, having given your entire life, your labor, your health, quite possibly your children's whole futures, toward a destination you will never see. An arrival that belongs, completely, to people who haven't been born yet. Nearly everyone who lives and dies aboard a generation ship is working toward a goal that offers them, personally, nothing back. Every ordinary human motivation we take for granted, the promise of a better home, the hope of seeing a new world with your own eyes, the simple comfort of knowing your effort mattered to your own life, is absent for almost everyone who would ever live aboard a ship like this. Something else has to fill that space instead. A kind of purpose that asks a person to serve a future they'll never personally benefit from, held up not by any one person's ambition, but by whatever culture the ship manages to build and pass down, generation after generation, convincing each new arrival that this life, sealed, inherited, unchosen, is still worth living all the way through. This isn't a problem propulsion can fix, or better shielding, or a smarter life support system. It sits underneath all of it, quietly, every single year of the journey. And it leaves one uncomfortable question hanging in the air with nowhere to land. Who exactly is responsible for making sure that purpose survives, generation after generation, when the people deciding that today will never live to find out whether it worked? Every government humanity has ever built existed inside a wider world of alternatives, other nations to compare itself against, rivals to lose ground to, citizens who could, in the worst case, simply leave. A generation ship's government would have none of that, just a sealed hull and vacuum on every side of it. It's worth looking honestly at how long human institutions actually tend to last, even with all those advantages in place. The Roman Republic, one of history's most studied political systems, held together for roughly 480 years, from its founding around 509 BCE to its effective end under Augustus in 27 BCE. That's a genuinely long run, longer than most nations manage, but it didn't end through outside conquest. It came apart from the inside, through a slow accumulation of civil war and concentrated power, ambitious men gradually hollowing out the Republic's institutions while carefully keeping their outward forms intact, so that for a while, most Romans thought they were still living in a republic long after they weren't. Iceland's Althing, often called the oldest continuously surviving parliament in the world, traces back to 930 CE. Even that celebrated example carries an asterisk. It was suspended for roughly 45 years under foreign occupation before being restored, a real gap in what people still call an unbroken line. Researchers who study how long institutions actually survive, measured rigorously across history, found something sobering. Looking at genuinely continuous political and cultural eras across major civilizations, the average length came out to only around 500 years, even among history's longest-running, most celebrated examples. Human institutions, even the best ones, even under Earth's comparatively forgiving conditions, trade, migration, outside influence, room to fail and be rebuilt, rarely hold their original shape and legitimacy for more than a handful of centuries before something fundamental gives way. Now think about what a generation ship's government is being asked to do. Stay legitimate in the eyes of a population who never chose it, for at minimum 2 to 3 centuries, without a single election anyone outside the hull has ever witnessed, without a rival government to measure itself against, without the option of citizens simply leaving if they lose faith in it. On Earth, a corrupt or failing government eventually faces pressure from outside, other nations, international opinion, the simple possibility of emigration. None of that exists aboard a sealed ship. Whatever government forms in year one has to either stay legitimate purely on its own internal merits for centuries, or successfully reform itself from within, again and again, without any of the outside checks that have historically forced reform everywhere else in human history. This is, quite literally, a governance problem with no precedent. Not because humans have never built lasting institutions, because every lasting institution humans have ever built did so with an outside world still pressing in, still offering comparison, still providing an escape hatch. A generation ship removes all three at once, for a population with nowhere else to go and no one else to measure themselves against. Every system this exploration has walked through so far, the air, the hull, the propulsion, the genetics, the government, wears down according to the exact same underlying law, whether it's alive or not. In the early 1970s, a Princeton physicist named Gerard O'Neill set his undergraduate students an unusual assignment: design a livable structure in space, large enough for real people to spend their entire lives inside, and make the physics actually work. What came back became one of the most detailed blueprints ever drawn for exactly the kind of vessel a generation ship would need. A cylinder, spinning. Spin solves a problem nothing else easily does. Without gravity, a body slowly wastes away, the way an earlier part of this exploration has already shown. But you can't carry gravity along with you the way you carry water or fuel. You have to manufacture the feeling of it, and the only method physics currently offers is rotation. Spin a cylinder fast enough, and anyone standing on its inner surface gets pressed outward, against the wall, hard enough to feel exactly like standing on solid ground. The physics is genuinely simple. Acceleration equals the radius of the spin, multiplied by the square of how fast it turns. Get the numbers right, and the inner surface feels like Earth. Get them wrong, and it doesn't. O'Neill's own design called for a cylinder roughly 32 kilometers long and just over 3 kilometers in radius, spinning at a slow half a rotation per minute to produce something very close to standard Earth gravity along its inner surface. The scale itself tells you something. This isn't a spacecraft in the way we normally picture one. It's closer to a habitable tube the length of a small country's coastline, engineered to feel, from the inside, almost exactly like standing outdoors. Here's where the engineering gets genuinely difficult, though, in a way pure math doesn't fully capture. Spin fast enough to produce real gravity in a small radius, and something called the Coriolis effect starts working against you. Walk in a straight line inside a rotating structure, and from your own point of view, your path curves, sometimes enough to cause real disorientation, nausea, a sense that the room itself is subtly tilting whenever you turn your head too quickly. Researchers studying human tolerance for rotating environments have generally found that keeping the spin rate under roughly 2 rotations per minute keeps that effect below the threshold most people notice in ordinary daily movement, which is precisely why O'Neill's design, and most serious generation ship proposals since, favor an enormous radius over a fast spin. A slower, gentler rotation across a much larger circle produces the same gravity with far less of the disorienting sideways drift. None of this is science fiction. The physics is understood, tested in centrifuges, modeled extensively across decades of published research. What's never been tested is the engineering at true generation ship scale, spinning continuously for centuries, its bearings and structural joints absorbing that rotational stress every single hour of every single day for the ship's entire operational life. Every earlier problem this exploration has covered, structural fatigue, redundancy, the slow compounding of small tolerances drifting out of spec, applies here too, except now it's not just holding pressure against a vacuum. It's holding an entire spinning structure together, generation after generation, so that a child born aboard can simply stand up one morning without ever once wondering why the floor is still beneath her feet. There's a word for what's happening to every single system on this ship, all at once, all the time, and the word doesn't care whether anyone is watching. Entropy. You don't need the equation to feel what it means. Left alone, closed systems drift toward disorder. Not violently, not all at once, just steadily in the same direction, day after day. whether the ship's lights are on or off, whether anyone's awake to notice or not. A machine wears down, whether it's running or sitting idle. A structure fatigues, whether it's under heavy load or resting quietly in the dark. There is no version of this voyage where things simply hold still. Every hour that passes is an hour in which something, somewhere aboard, has degraded slightly further than it was the hour before. Repair slows that process. It never reverses it. A replaced part isn't really a new part, not in the deepest sense. It's a temporary correction, borrowed from a finite store of raw material and labor the ship carried with it from the very beginning, a store that can never be replenished from outside. Fix one failing system, and the resources spent fixing it are resources no longer available for the next failure, and the one after that, stretching forward into a future none of today's engineers will live to see. This isn't pessimism, it's arithmetic. The same arithmetic governing every closed system anywhere in the universe, from a dying star to a leaking faucet. The smaller failures matter more than they seem to, because they rarely arrive one at a time, with room to breathe in between. They compound. A single worn seal, a single degraded filter, a single tolerance drifting slightly out of spec means almost nothing on its own. But across 100 years, 1,000 small tolerances drifting the same direction at the same time in systems that were never designed to run this long without a dry dock and a fresh set of outside hands, start interacting with each other in ways no engineer, however careful, could have fully modeled in advance. This is the quiet, unglamorous truth sitting underneath everything this exploration has examined so far. Not one dramatic failure, a hull breach, a fire, a catastrophic accident, though any of those stay possible the whole way. Something slower, something that looks, from the outside, like nothing happening at all, for centuries, until the accumulated weight of 10,000 small, patient degradations finally becomes the thing that decides whether the ship, and everyone aboard it, actually arrives. Somewhere aboard, right now, in whatever year this is for them, a maintenance log is being updated by hand, one more small entry in a book that has been kept, unbroken, for longer than anyone alive can quite account for. Step back now, far enough to see the whole picture. Even a ship that survives all of this completely, that holds its air, its hull, its government, its people, all the way to Proxima Centauri, has still barely moved anywhere at all. Our galaxy, the Milky Way, stretches roughly 100,000 light-years across, a disk of hundreds of billions of stars. Our sun just one faint point among them, adrift about halfway out from the center, in an unremarkable spiral arm nobody would notice from any real distance. A generation ship crossing to Proxima Centauri travels 4.24 light-years. Set against the galaxy's true width, that's a little more than 0.04% of the whole diameter. The fastest object humanity has ever built, the Parker Solar Probe, moves at roughly 690,000 kilometers an hour, faster than anything else humans have ever made, close enough to the sun that its heat shield glows white. At that speed, crossing the Milky Way would still take something on the order of 1.5 billion years. Longer than complex life has existed on Earth, a generation ship, centuries in the making, carrying a sealed civilization across a gap that already strains the outer limits of what's survivable, is still only crossing a rounding error of the galaxy it calls home. There's something almost peaceful in that, once the scale actually settles in. The ship isn't really going anywhere, not by the galaxy's own measure. It's simply moving, slowly, deliberately, through an emptiness so vast that even total success looks, from any sufficiently wide angle, indistinguishable from staying perfectly still. No one watching from far enough away would even see it move. From outside, from some hypothetical vantage, 1,000 light years off, the whole voyage, launch to arrival, hundreds of years of human lives lived and lost inside a metal hull, would look like nothing at all. A single point of light, holding almost perfectly still against a field of 100 billion others. And the isolation only deepens the further the ship travels. Once a generation ship passes a certain distance from Earth, rescue stops being a real possibility in any practical sense. Not unlikely, not difficult, genuinely absent for every remaining year of the voyage, for everyone born after that threshold gets crossed. There's no Coast Guard for interstellar space, no signal that reaches home and comes back with help in any time frame that matters to whoever sent it. A distress call from the far side of the journey wouldn't reach Earth until long after everyone who sent it, and everyone who might have answered, was gone. The silence out there isn't empty of meaning. It's simply larger than anything a human voice was ever built to cross. Humanity has already sent something out into that exact silence, decades ago, and it offers the closest real answer we have to what a journey like this actually looks like, stretched out across time. Our galaxy, the Milky Way, stretches roughly 100,000 light-years across, a disk of hundreds of billions of stars. Our sun just one faint point among them, adrift about halfway out from the center, in an unremarkable spiral arm nobody would notice from any real distance. A generation ship crossing to Proxima Centauri travels 4.24 light-years. Set against the galaxy's true width, that's a little more than 0.04% of the whole diameter. The fastest object humanity has ever built, the Parker Solar Probe, moves at roughly 690,000 kilometers an hour, faster than anything else humans have ever made, close enough to the sun that its heat shield glows white. At that speed, crossing the Milky Way would still take something on the order of 1.5 billion years. Longer than complex life has existed on Earth, a generation ship, centuries in the making, carrying a sealed civilization across a gap that already strains the outer limits of what's survivable, is still only crossing a rounding error of the galaxy it calls home. There's something almost peaceful in that, once the scale actually settles in. The ship isn't really going anywhere, not by the galaxy's own measure. It's simply moving, slowly, deliberately, through an emptiness so vast that even total success looks, from any sufficiently wide angle, indistinguishable from staying perfectly still. No one watching from far enough away would even see it move. From outside, from some hypothetical vantage, 1,000 light-years off, the whole voyage, launch to arrival, hundreds of years of human lives lived and lost inside a metal hull, would look like nothing at all. A single point of light, holding almost perfectly still against a field of 100 billion others. And the isolation only deepens the further the ship travels. Once a generation ship passes a certain distance from Earth, rescue stops being a real possibility in any practical sense. Not unlikely, not difficult, genuinely absent for every remaining year of the voyage, for everyone born after that threshold gets crossed. There's no Coast Guard for interstellar space, no signal that reaches home and comes back with help in any time frame that matters to whoever sent it. A distress call from the far side of the journey wouldn't reach Earth until long after everyone who sent it, and everyone who might have answered, was gone. The silence out there isn't empty of meaning. It's simply larger than anything a human voice was ever built to cross. Humanity has already sent something out into that exact silence, decades ago, and it offers the closest real answer we have to what a journey like this actually looks like, stretched out across time. In 1977, humanity launched the closest thing we've ever sent toward this exact question. Not a generation ship, nothing built to carry people, just a single robotic probe, roughly the size of a small car, carrying 10 scientific instruments and a plutonium power source designed to keep it running for about 5 years. Voyager 1 has now been operating for nearly 50. It flew past Jupiter in 1979, past Saturn in 1980, and then kept going, long after its original mission had already been completed and declared a success. In 2012, it became the first human-made object to cross out of the heliosphere entirely into true interstellar space, the same boundary a real generation ship would eventually have to cross and keep traveling through for centuries, with living people aboard instead of a camera and a radio. Consider what 50 years has actually done to this machine. Its power source, a radioisotope thermoelectric generator turning the heat of decaying plutonium into electricity, loses roughly 4 watts of output every single year. A slow, steady decline no repair crew will ever reverse, because no repair crew will ever reach it. One by one, NASA's engineers have had to shut down Voyager 1's instruments to conserve what little power remains, not because anything failed catastrophically, but because the numbers simply stopped adding up. Its cameras went dark decades ago. Its cosmic ray subsystem shut off in February of 2025. Its low-energy charged particle detector, which had run almost continuously since launch, was switched off in April of 2026. As of today, only 2 of its original 10 instruments still function, a magnetometer and a plasma wave detector, kept alive purely because engineers on the ground keep making careful, deliberate choices about which small piece of the mission gets to keep breathing and which one has to go quiet permanently to buy the rest a little more time. Humanity's most successful, most enduring deep space machine, the single best real-world data point we have for what it means to survive in true interstellar space, is a machine the size of a car, unmanned. No life support, no crew, no reproducing population, and it is still, after everything, slowly dying by inches, 1 watt and 1 instrument at a time. Now place that image next to a generation ship. Not a car-sized probe with no biological needs, but a sealed vessel carrying tens of thousands of living people, their air, food, water, culture, government, genetics, all of it required to keep functioning, uninterrupted, not for 50 years, but for centuries, without a single team of engineers on Earth ever sending a command to help. Voyager 1's slow fade isn't really a story about failure. It succeeded, spectacularly, far beyond anyone's original expectation. It's a demonstration of just how much even a triumphant, brilliantly engineered mission still eventually loses to entropy, given enough time, enough distance, enough silence. You are not aboard a machine like that, not yet, but it's worth sitting, for just a moment, inside what that kind of distance would actually feel like, from the inside, in a body instead of a signal. An old man aboard the ship, well into his 70s, presses a hand against the wall to steady himself on the way to breakfast, the way he's done every morning for years now. His grandchildren don't know a version of him that didn't need to. He doesn't remember one either. Whatever his bones were like as a younger man, in a younger version of this ship, has simply become a story he no longer entirely trusts. Even if every mechanical system aboard held perfectly, even if the government stayed legitimate and the genetics stayed healthy and the knowledge kept transferring cleanly from one generation to the next, there would still be one more system quietly working against the mission, and it wouldn't be part of the ship at all. It would be the human body itself. We already have real measurements of what happens to a body that spends extended time away from Earth's gravity, gathered from astronauts who've spent months, not centuries, aboard the International Space Station. Bone remodels and weakens at a documented rate of roughly 1 to 2% per month in microgravity, and even with a strict daily routine, about 2.5 hours of exercise, 6 days a week, built specifically to fight this exact effect, astronauts still return from a typical 6-month mission, having lost an average of around 3% of bone density in the lower spine and roughly 6% in the hip. The best countermeasures medicine currently has, applied rigorously, only slow the loss. They don't stop it. Muscle tells a similar story. Losses on short missions run 10 to 20%, and research suggests that without serious, sustained countermeasures, that figure could climb as high as 50% on longer ones. Now sit with what this means for a generation ship. If artificial gravity, most likely produced through rotation, isn't part of the design, or fails, or degrades over centuries the way every other mechanical system aboard eventually does, an entire population could spend generations slowly losing bone density and muscle mass, compounding across lifetimes, lived entirely without the gravitational loading the human skeleton evolved to expect. Even with artificial gravity working exactly as intended, we're still relying on decades, not centuries, of medical data, gathered from adults who spent months away from Earth, not from children conceived, carried, born and raised their entire lives inside an environment their species never evolved for. And here's where the honest, scientific answer has to stop, rather than speculate further. No human being has ever lived an entire life, from birth to death, away from Earth's gravity and biology. Nobody knows, with any real confidence, what multiple successive generations of that experience would do to bone development, to a fetus developing in altered gravity, to cardiovascular health sustained across a full lifespan instead of a single mission. This isn't scientists disagreeing on an answer. It's a case where the actual experiment, the only one that could answer it honestly, has never been run, because running it would require exactly the kind of multi-generational, multi-century voyage this whole exploration has been circling from every other angle. The old man reaches the mess hall, sits down across from his granddaughter, and eats breakfast the way he has for decades, in a body slowly, patiently, permanently shaped by a world with no real ground beneath it. Say the ship survives everything. The air holds, the hull holds, the genetics hold, the government, against every historical precedent, somehow holds too. 250 years pass, and the ship finally reaches Proxima Centauri, decelerates successfully, and settles into orbit around whatever world it came to find. Here's the detail almost nobody accounts for when they imagine that moment as the ending. Arrival isn't the ending. It's the start of an even longer problem. Unless the destination world already has a breathable atmosphere, drinkable water, and a temperature range human bodies can survive, which no confirmed exoplanet discovered so far actually offers, the ship's population can't simply walk outside and begin a new life. They would need to terraform it first, and the real research on how long that actually takes should sober anyone picturing a quick, triumphant landing. NASA scientists studying Mars, our own solar system's best candidate, and by far the easiest terraforming target humanity has, have modeled the process in 2 distinct phases. The first phase, warming the planet and thickening its atmosphere with carbon dioxide, is the fast part, and even that could take on the order of a century. The second phase, building an atmosphere with enough oxygen for humans and animals to breathe normally, is the genuinely difficult part. Published estimates for that phase run to 100,000 years or more, using any technology currently considered plausible. Other independent analyses studying full-scale terraforming of an actual exoplanet, not the comparatively convenient case of Mars, arrive at similarly staggering numbers, sometimes citing a more optimistic minimum of 1,000 years, sometimes landing closer to that same 100,000-year range once the full atmospheric chemistry is worked out honestly. Consider what that means for the generation ship's population the moment they arrive. 250 years to get there, potentially thousands, or tens of thousands, of additional years before the world outside is actually safe to breathe unassisted. Arrival doesn't end the sealed, self-contained existence this entire exploration has been examining. It just moves that existence into orbit around a different star, or onto the surface in domes and pressurized habitats functionally identical to the ship they just spent centuries aboard, while a terraforming project even slower than the voyage itself grinds forward across additional centuries, run by descendants of descendants of descendants of whoever first stepped off the ship. Somewhere in that far future, a child will be born in one of those surface domes, and she'll press her hand against the dome's transparent wall, the way children on the ship once pressed their hands against portholes, looking out at a sky the color of somewhere else, waiting for air she still won't be able to breathe without help. The ship, in a sense, never really ends. It just changes shape. The ship's own name starts to look different, held up against that timeline. Not a vehicle that delivers its passengers to a destination. A way station between one closed system and the next one, longer and slower than anyone standing at the original launch site could have possibly imagined, back when the whole voyage still looked, on paper, like the hard part. You're listening to these words somewhere warm, on a planet that has never once had to manufacture its own air, orbiting a sun that has never needed a backup. That fact alone, ordinary as it feels lying there right now, is the quiet luxury every person aboard a generation ship would spend their entire life without. So how long could a generation ship actually survive in deep space? The honest answer, gathered from everything real science and real history can offer, is that the ship itself, the hull, the engines, the air, might plausibly hold, given enough redundancy, enough careful engineering, enough centuries of patient maintenance. Machines can be overbuilt, systems can be duplicated. Given enough foresight, hardware can be made to outlast almost anything humanity has built before it. The metal was never really the fragile part of this equation. The people are. Walk back through everything this exploration has covered. The genetics, thin enough that Earth's own island communities already showed us the cost of a shrinking bloodline. The government, asked to stay legitimate for centuries, with no outside world left to answer to. The purpose itself, handed down to generation after generation, who never chose any of this, who have to be persuaded, quietly, again and again, that it's still worth continuing. A ship can be engineered against entropy far more successfully than a civilization can ever be engineered against forgetting. Picture someone aboard, 4 generations deep. They've never seen a horizon, never felt wind on their skin. Everything they know about Earth arrives secondhand, a story passed down by people who were themselves only ever told the story, never shown it firsthand. And still, most mornings, they wake up anyway, do the small, unglamorous work their life requires of them. Choose, in whatever quiet way a person chooses anything, to keep the ship and everyone on it alive for one more day. Not because the destination means anything to them personally. It doesn't, and it never will. But because somewhere back along the long chain of people who came before them, someone decided that continuing mattered more than understanding exactly why. That, in the end, is what the ship is actually testing, not its hull. Not its engines, whether meaning itself can survive the crossing, unsupported, unrepeated, generation after generation, alone in the dark. The stars don't wait for anyone, but somewhere out there, if we ever go, someone will still be walking toward them anyway.